This is the second video I'm doing on the GPS disciplined oscillator. I'm going to go over some of the theory on what's going on, how it works, why it works. So basically, what we're trying to do is we're trying to have a clock which generates 10 megahertz signal, and that's every second. And our notion of a second comes from the GPS. So I have 10 megahertz oscillator, I have the PPS signal from the GPS, and basically this is the oscillator clock. As it clocks, I can measure how many clocks it makes in a counter. That counter goes every second from 1 to 10 million. So here is the clock edge coming, and a little bit after the clock edge, just theoretically, I get a count. So it starts 1, 2, 3, and so forth, all the way up to 99999. Clock edge comes, I'm at 10 million, and then it goes back to 1. Every second, the PPS comes along. That's my look at the count. And if that count is 10 million every time it comes along, then I know that I'm at the proper frequency. And as you see here, I sample it right before it changes, so it's 10 million, and I sample it again right before it changes, and it's 10 million, so I know that everything's perfect. Now, in the real world, my clock isn't perfect. It can run fast or slow. So as an example, if it's running slower, that means that these edges are wider, and so that means that this whole section moves over relative to the perfect second. So in this case, when my PPS comes along, I sample it right after it changes. So that's slow. And so even though I still get 10 million, I'm running slow. I'm not really going at the proper speed. So in the perfect world, in this example, 10 million is really 99999 plus a little bit to actually 10 million. And so basically, in the circuit, any fractional count measured is just rounded up. So this becomes 10 million. And one count is 10 nanoseconds at 10 megahertz. So that's the perfect world. It's not perfect. The PPS instant is actually plus or minus 10 nanoseconds. And so if in this case, here's the count moving up and here's where my PPS comes, it can actually come plus or minus 10 nanoseconds. So there's a 20 nanosecond spread, which leads to an error of my measurement of 0.1 hertz, which is plus or minus 10 parts per billion. So if I'm in the middle here, the jitter doesn't matter. If I'm near an edge, when the PPS is jittering, I'll get an inaccurate count. And so there's two factors I have to take into consideration. One of them is this fractional error. Other one is the PPS jitter. Now, I've looked with an oscilloscope, and the jitter isn't 20 nanoseconds back and forth fast. The plus and minus 10 nanosecond PPS is at about a 10 hertz rate. 10, not 10 hertz. It's at a 10-second period. So if you were to look at it, if here's the error in nanoseconds up and down, and this is time, it kind of it wanders back and forth as the GPS control loop controls it. And I don't know if it's a sine wave or if it's a triangular wave, but second on second, it doesn't move that much, and you can see it just sort of roll back and forth. So it's sort of like this. The PPS jitters due to the nature of GPS clocks. So, these clocks, they're not right here at the table next to me. They're up in the sky, and, depending on how close or how far they are, that affects how long the signal takes to get to you. And, that orbit, it has a variation, and we know where they are, kind of. There's uncertainty there, and that's part of the prediction. The other thing about this clock is that because of general relativity, the clocks run fast. It's half a nanosecond. Sorry, yeah, they run fast. Half a nanosecond per second at their altitude, because time runs slower closer to the mass of the Earth. And then they're moving fast, so special relativity says their clock actually slows down. So that effect is 0.15 nanoseconds per second. So the clocks actually drift a lot, which they actually correct for. There's also atmospheric propagation variation. So the fact that it's not traveling through free space, so the signal takes time. So there's a lot of noise in there, but it gives you a plus or minus 10-second variation. So how do we deal with these things? Well, the circuit that we're using, it's a 10 megahertz clock, which goes into a counter, which I sample every PPS, and the sample is S per N, so N is the number of the sample. So the count is the current sample minus the last one, so that's the change, and so it should be 10 million every second, and the error is the count that I get, the 10 million minus the expected, which is 10 million. So if I get 10 million and one every cycle, or here if I get 10 million.3, it's fast. But again, because of what I described with the rounding factor, this would show up as 10 million and one. So what happens is if you look at a series of counts, and so here I keep them going continuously. If I say we're going at 10 million.3 hertz, each subsequent count increases, and as you see when I do the math, when I theoretically do the math, that I have a delta of here 10 million, because I'm not counting the fractional part, but all of a sudden I get 40 million and one. And so when I do the math, I get 10 million and one, and then when I get 50 million and 1.5, that delta, I'm not looking at these lower digits, it's back to 10 million. So my error term actually shows the fractional effect if you observe it over time. And this can be seen that, here's the count, here's the PPS signal coming in, here's the count at 10 million. This is that, quantum here that I was showing. And since this is running fast, it's sliding relative to the PPS. That's why I get 10 million, I see 10 million elapse, I see 10 million elapse, and then here the 10 million has already happened, and now I'm at the next count, which is shown here, a 1. And so that's why it slips, and that's why I can, even though I'm not taking care of the fractional part, it shows up over a long period of time. It also sort of illustrates that I don't know why you need all these digits up here. You only need enough digits to capture the expected error and deal with the math underflow, overflow. So for an example, this is what I was talking about when I was going to eliminate one of the I/O expanders, is that if the frequency is 7 and the error is plus or minus 2, you only need to keep track of one digit. So here in the example, the counts would be 0, 7, 14, 21, 28, 34, 40. And, this is up 7, up 7, up 7. This is up 6, up 6, up 8, up 6, and so forth. If I do the math, figuring out the count here is easy. It's 7 minus 0, which is 7. This is, it's 14 minus 7, but if I only have the bottom digit, since 4 is less than 7, I have to put a tens there, so it becomes a virtual 1 plus 4, so that's 14 minus 7. This is 21. I have a 1. 1 is less than 4, so I have to, put in the virtual 10, so it becomes 11 minus 4 and 7, and so forth. And you don't care that this is really a 2 or a 3 or a 4, because the amount that it can be under is always off by that factor of 10. So as for example, if the frequency was 17 each time, 10 won't work, because I'd go 7, 24, 41, and actually when I do the math here, this isn't 14 minus 7, it needs to be 24 minus 7, and so I need to borrow a 2. So the rule here is that you need to have as many digits, or the increment of the digits has to be in relation to what the expected the frequency is going to be. So if you look at it in terms of the math, my current count, it's a number that's 10 million plus or minus some range. And the range that I've observed with the system here is when it's warming up, it's plus or minus 200. The normal tuning error is plus or minus 7. So, a count, it's going to be 10 million plus or minus, wherever that range is, minus the previous sample. And if I make that sample, let's say I make the sample 3 digits because it's plus or minus 200 here. So the error that you calculate, when you do calculate, it's 10 million plus or minus the range, which is what the count is, minus the previous sample, minus 10 million, which is the expected value. So the 10 millions actually cancel out. And what you're left with is the error is basically the range minus the previous sample, which is 3 digits. And here my rule, I have to add 1,000 if it's going to underflow. So that's why I only need the first IO expander for the tuning range that I'm going to plan for. And so at 10 million in hex, it's 98, 96, 80, and so my factor that I add, so 1,000 is actually 80 hex, which is 256. So this makes up for a 256 count error, which is, well, smaller than the range, but I don't care when it's warming up. So when it's warming up, the error is going to be wonky. But when I'm in the normal tuning range, having a working range of 256 with an actual range of 7 is going to be fine. So we handle the fractional part by taking multiple samples, and then we learn that we can discard the higher order digits to simplify the circuit. So the PPS jitter is also handled by multiple periods. So here I'm showing a perfect PPS and then a real PPS with jitter. So here the count, this is 10 million going to 10 million 1, 20 million going to 20 million 1, 30 going to 30 and 1, 40 going to 41. Normally, if I sample that with a perfect clock, I always hit the 10, 20, 30, and 40 million, so I see that the interval is 10 million. If the PPS is jittering, so here it samples it normally at 10 million, then it samples it jittered over, so now it's at the +1, and then it goes back to its nominal setting, and it's still at its nominal setting. The samples that we get here are 10 million, we get 10 million plus 1 here, and we get 30 million, and we get 40 million. So if you calculate the counts, I get 10 million for the count here, I get 10 million plus 1, 20 million plus 1 minus 10 million, and here I get 30 million. When I do the math, I get 10 million minus 1, and then here I get 10 million delta. So the error I see, it's +1, then -1, then 0. So with a perfect clock, when I jitter near this boundary, I'll see a +1, -1 pair come in. So, how do I know that that's not the actual error of the system? So the typical error ranges are, well, if it's greater than plus or minus 10, that's a warm-up, loss of GPS or noise. If it's between 2 and plus or minus 2 and 9, that's why I'm doing my coarse tuning. And so I really don't care about a plus or minus 1 of this jitter. And if my error that I get is a plus or minus 1, I'm in the multiple period tuning. So I'm going to look at how many times it's 0 before going to something that's not a 0. And when I'm doing that, I can distinguish a jitter from just the error, because the error is always going to be +1, then a bunch of zeros. It's not going to go -1, a bunch of zeros, then +1, a bunch of zeros. The oscillator is too stable for that. So here's some examples. Here, it's a nominal case. I'm 0, 0, 0, 0, +1, 0, 0, 0, 0, +1, 0, 0, 0, +1. And so I'm high by 0.2 hertz. And so there's one slip every 5 seconds. This is when my clock is going too fast. If, on the other hand, I see like a +1, a 0, a +1, -1, +1, then a bunch of zeros, this, and these are the GPS slips that I can chalk this up to being the jitter. Or if I see a 0, 0, +2, -1, 0, 0, +1, that this was a slip of the clock that occurred at a PPS jitter event. And so software is smart. It can figure this out. If I'm always +2 off, I'm doing my coarse tuning, so I don't care about the jitter effect. So that takes care of that. How do I get to highly accurate? So if my error is in the range of 10, I'm at 1 ppm approximately. If my error is kind of 0, I'm at 0.1 ppm. That's without PPS jitter. If I'm 0 for 10 seconds, I'm at 10 parts per billion. And if I'm at 0 for 100 seconds, I'm at 1 part per billion. And my goal is 1 part per billion-ish. So how does this PPS jitter affect things? Well, at 1 second, the PPS jitter is 20 nanoseconds maximum. So that gives me, 0.2 hertz when I counts when I should be getting 10 million. So that's where I get an error of 20 parts per billion, which is greater than my goal. If I sample for 10 seconds, the maximum jitter is still 20 nanoseconds, but now I'm looking at that over 100 clock cycles. And so my error is 2 parts per billion. And at 10 nanoseconds, the accuracy of my measurement of my clock, it's 10 parts per billion. So the error from the jitter is now less than the error of my clock accuracy. And at 100 nanoseconds, where I can potentially measure 1 part per billion, the jitter contribution is 0.2 parts per billion. So it's no longer a factor. So PPS jitter, it's not a factor for this. What I have to do, the ultimate accuracy of what I do will be based on a thermal stability, because there's a thermal component here, which is, I think, plus or minus 10 parts per billion over temperature range. So I'm going to insulate and monitor the temperature for that. The voltage stability, I think that was plus or minus 2 parts per billion. So I'm going to isolate and filter whatever touches the DAC or the oscillator. And that, control voltage stability also. Isolate it and filter it. The oscillator has ultimate stability, and I think that is 0.1 parts per billion. And that just got cured with money because the oscillator is, $100. And then the stability of my algorithm, because my algorithm might want to go in there and tweak stuff. And that's just having a smart algorithm. And so, if I can, finely tune the control voltage and it stays 0 for, 100 seconds, I'm good. And just playing around with it, it's been 0 for, tens of seconds at least. And so I think I can meet my goal. And when it did vary, it was probably because, the heat came on, or the window was open, or, I blew on it. So I haven't done much to the actual hardware, but I did change one piece of software. So if I boot this up, you're going to see, here's the new software. So this extra digits here, that is the calculation of the error term based only on this I/O expander. And so I still have a loss of GP. I can now I have my fix. And so my error for real, it's 199, but I think it's my error term is wrong because it's too high for the calculation. But as it warms up and the oscillator goes faster as it warms up, and there's a glitch, as it speeds up, and so now it's within 128 of the actual value, then my truncated thing will work. So if you noticed, when this was over 128, that was some wonky value. Once it went under 128, it's fine. That's because I'm taking the last 8 bits, which is 256, and then it's binary, so 0 is actually in the middle. So anything over 128 is a negative number. So this tracks. And so actually it's doing exactly what it should. And actually, when I saw what I thought was the glitch, it might be a math long issue with actually the math in the chip, not necessarily is a calculation issue. Oh, yeah, actually, no, it's not a calculation issue. These last bits get munged by some timing issues we'll talk about in the next video, and that's why I calculate the count wrong. But since I'm only looking at these bits, I do not have that timing issue So this is always going to be accurate. So that fixed, there's the glitch. It did not affect these bits. It only affected these upper bits. I know exactly what's going on, and I'll explain that in the next video. So it's good progress, and thanks again for watching.